Okay, this video is part of the amath481 course in autumn of 2016 at the University of Washington. And in this video, I'm just going to give an overview of the 2D fluid solver that we're going to be doing for the second homework assignment. Okay, so we're solving the fluid equations in vorticity stream function formulation. So vorticity is denoted by omega here, and the stream function is given by psi. So it's kind of the standard fluids equation format. So we've got an effective term, which is given by this bracket, which is bracket of psi omega is psi x omega y minus psi y omega x. And then you have this diffusive term given by nu Laplacian omega. So this is the evolution equation for omega. And at any given point in time, we can recover psi by solving Poisson's equation. Okay, so minus Laplacian psi equals omega. Okay. And as we've pointed out before, we want to solve this on a periodic domain. So that means that, among other things, we need zero net vorticity. And also, because of those boundary conditions, the periodic boundary conditions that we're imposing on psi, this equation only determines psi up to a constant. So that constant doesn't really matter because in the evolution equation for omega, we only use derivatives of psi. Okay. So that's the basic setup. And what we'd like to do is to solve this numerically. And we're going to be using MATLAB's built-in ODE solver, ODE45, which uses the Runge-Kutta-Feldberg method. And for that method, we need to be able to write a function f of omega, okay, so that dt omega equals f of omega. And so in this setting, this is f of omega. And right, I mean, here we're kind of interpreting things continuously, but right, this right-hand side will eventually be represented by the values of omega and psi on the grid and approximations of their derivatives on the grid. Okay, so we need to talk about how we can set up this function f of omega so that we can use ODE45 in order to solve the equation. Now, this is a little bit trickier than we've been doing before. In particular, we're going to have it take as input only omega. So first we have to recover psi, and then we can do the time stepping. So I'm going to put the basic steps of how to evaluate f over here. So how to evaluate f of omega. Okay. And so as I said, the first step is we need to recover psi. So we need to solve for psi. And right, we said psi is related to omega through this Poisson equation. Okay. So that's the first step. And now once you have psi, the rest of the steps are actually quite simple in comparison. So the second step is we have all of these derivatives of our unknowns, right? We have derivatives of psi and omega, and we have the Laplacian of omega, which is just dxx plus dyyy. So we need to evaluate all those things. So evaluate psi x, psi y, omega x, omega y, and Laplacian omega. Okay. And then the final step, right, is just to combine these. So combine to get f of omega equals psi x omega y minus psi y omega x plus nu Laplacian omega. Okay, so right, I've kind of written things continuously here, but we're solving for the problem on a finite grid. Okay? And because of that, we can just use finite differences to approximate all of these different, we need to solve this equation, so we approximate the left-hand side here, and that gives us a matrix equation for the values of psi. So that's pretty standard in terms of finite differences. You just use the 5-point stencil over here, and then you would invert it. The trick is, for this setting, the 5-point stencil actually has a non-zero null space. So we'll talk a little bit about how we handle that. Okay. The next step is actually much simpler. Here we needed to solve a linear system, and down here all we need to do is evaluate derivatives. And so those are very straightforward. You just say psi x is given by the finite difference approximation of the x derivative of psi everywhere. Okay? And likewise for psi y, omega x, omega y, and Laplacian omega. In particular, right, to get the values of Laplacian omega using finite differences, you would just apply the 5-point stencil to the grid values for omega. Okay, and then, right, when you combine, that's just adding things together. So we're going to go through the code that is provided to you and talk about kind of how all of these steps are laid out. But first, let me erase all of this. Okay, so now let's look at the code. So here I've got the driver file that was included with the homework, and the first part of the code is pretty simple. It's just setting up the geometry here. L is the going to determine the width of the box that we're solving on, so it goes from minus L to L, and then minus L to L. Okay. N is going to be the number of grid points in each direction, and that leads to a total of n squared grid points on the entire grid. Nu is just our diffusion parameter. And then we'll set up some kind of time discretization. So we have a start and stop time. And this NT here is the number of times that we're going to just request the solution from ODE 45. It's not how many steps we're going to request that ODE 45 uses. So ODE 45 is adaptive. It determines its own time steps. What this says is I want the solution at all these different times so I can kind of watch it like a movie. And the reason you want to do this is that for a sufficiently difficult problem, ODE 45 will take many, thousands and thousands of time steps, and you'll soon run out of storage if you were to store each and every solution time. So really we're going to request it this pretty finite number of times. Okay. And so, right, those times here are just equispaced between t0 and the final time, capital T. And then we set up our spatial discretization with equispaced points. We only keep the first n of them because the last one is periodic, so it's equal to the first. And then in the y direction, because it's the same limits, we use the same points. We call mesh grid to give ourselves now a grid of x and y values. So within that grid, right, as you move down the column, the y values change. And then as you move over in a row, the x values increase. That's just the convention that mesh grid uses, so we'll keep it. And then here, we can also form vectors which correspond to those values using reshape. So that's how we'll always define vectors defined on our grid. And then here I've got how I'm going to set up the initial condition, right? Because this is an initial value problem, we need to have a starting vorticity. And so we need also for that starting vorticity, as we discussed before, to have 0 net vorticity, and so it needs to integrate to 0, and it should be periodic. Okay. So we can set up functions which are roughly periodic. So if you choose Gaussians, right, which decay sufficiently by the time that you get to the boundary, then it appears to be periodic for all intents and purposes. So we're going to set up Gaussians centered at all of these points. They're kind of chosen more or less arbitrarily by me. And then we give them different strengths. And the key here is that all of these strengths add up to 0 so that the integral of the total vorticity will be 0. Again, this is just setting the initial vorticity, right? We've used those mesh grid values xx and yy. And then we can now plot using a heat map. That's what p color does to see what the initial condition looks like. So let's plot that real quick. Right, so this is just what the initial condition is going to look like. Those are those kind of smaller strength Gaussians, but we have 2 of them, and then this one is twice the strength and opposite sign Gaussian. So this is kind of the starting vorticity, and in the rest of the region, it's about 0. Okay, so let's get back to where we were in the code. Okay, so right here is where we were looking at what the initial condition looks like. And then now we're going to set up some finite difference matrices. Actually, I'm going to come back to this in a little bit after we look at where they're needed. Okay. So the heart of the code is down here. Okay, well, so first we reshape omega to be a vector, right? Because ODE45 is expecting a vector. Okay. And then, right, the heart of the solver here is we call ODE45 with a given right-hand side function f. Okay, so we've called it f vort stream here. And so if you look in the code, we have f vort stream for a given time t and omega, right? We're setting up a function handle for that. And then we pass it those parameters that we set up above. And we can come back to that. And then, right, we plug in t-span, that's where we want the solution, and omega 0v, that's the starting condition. Let me just close that. Okay. And then the output is going to be the times that we requested the solution and the solution at those times. And it's only going to give us omega because that's how we've set things up. We're doing the evolution for omega, and within f vort stream, we solve for psi at each time step. Okay, so let's look at the function f vort stream. And this will take exactly the form of the function f of omega that I outlined earlier. So here's f vort stream. The output is omega p, meaning omega prime, right? So that's f of omega. And it takes as input t, omega, and this params array. Yeah. So we loaded all of these things into the params array in the driver, and really it's just telling us kind of where we're at with the code. Right? In particular, we have L, which is the size of the grid. N is the number of grid points in each direction. Nu is the diffusion parameter. AX is the finite difference matrix, which corresponds to differentiation in the x direction. AY is for differentiation in the y direction. ALOP is the 5-point stencil. Okay. And then we'll talk about these L extended, U extended, P extended, Q extended. What they correspond to is the LU decomposition of an extended matrix, which has ALOP embedded within it. But it's extended in such a way that it's actually invertible because ALOP is not invertible. Okay? And so that matrix, this LU decomposition, corresponds to solving, right, the equation for psi. So we want to solve psi by inverting the Laplacian. Okay? So we had to make sure that the matrix that we set up for that is indeed invertible. Okay? Great. So the way that the code proceeds is that first it solves for Laplacian psi equals minus omega. Okay? So all you have to do is to use the extended system as you set up as omega 0. And I can explain that in a little bit. And then really you're just using kind of the standard LU decomposition way of solving this system. And then you have to interpret things a little bit differently because it's extended. So only the first up to right before the last entry actually gives us psi. And then we reshape psi because using this notation, it gives us a row instead of a column, and we wanted a column vector. Okay. So all this step is doing is it's solving for psi by inverting the Laplacian. That is, it's solving this Poisson equation here. Okay. And we'll explain exactly what system this is solving in a little bit. And then once you have psi, the rest of it is very straightforward. And it's straightforward because all you have to do is apply operators. You don't have to solve anything anymore. So to find the derivative of psi, which we'll call psi x here, you just multiply that matrix for finite differences, differentiation in the x direction by psi, the vector psi. So psi x is ax times psi y is ay times psi, and so on, right? So omega x can be obtained that way, omega y, the y derivative of omega, and then omega lop, which is the Laplacian of omega, is obtained by applying that 5-point stencil to omega. Okay. So a lot of these things should be pretty familiar here. This is kind of the one trickier step, and it's because of that, the fact that the 5-point stencil is not invertible when you're on a periodic grid. Okay. So down here now is the final step, right, where we said you just have to combine everything to get f in the end. So you have omega p is psi x omega y minus psi y omega x plus omega log. And one thing to be careful about here is we're doing dot times, and that means, right, the resulting vector for dot times is just each entry is the product of the entries in the two vectors that you have on either side of the dot times. Okay. And that's a thing to be careful about because sometimes you could have accidentally stored one of these as a row vector, and in that case, times would just give you the matrix multiplication result of that, which would be a scalar. So you have to be a little bit careful about that, but it's very straightforward. Okay. So that's what f-vort stream does. And it calls us at every time step. So one thing that I threw in here, even though f-vort stream doesn't really depend on time, I just I just spit out the time here by putting t without a semicolon, without suppressing the output. And so that kind of tells me how I'm progressing through the code. Okay. So if we go back to the fluids driver, we pass that function f-vort stream to ODE45, and then it chooses the time steps so that it can accurately integrate the solution forward in time. And that's about it. So how about I run this code? I might use the magic of filmmaking to speed up getting the solution, and then we'll see what the solution looked like for that initial condition. Okay. So we see it running here, and these are the time steps that the ODE45 solver is taking. As you can see, we're going all the way up to t equals 5, so this could take a little while. Okay, so we're almost there, and what you're going to see when it finishes is a heat plot of the vorticity with contours of the stream function overlaid on it. So that's what we're seeing here, right? The color gives us the vorticity, and the contour lines give us contours of the stream function. And so those two little chunks of vorticity that are of the same sign are rotating around each other, and they're actually kind of spinning into each other. And then the fact that you now have this kind of section of vorticity of one sign and a chunk of vorticity of the other sign means that they're going to kind of move together slowly. Okay, so that's, I find that kind of like a fun little video. And I encourage you guys to play around with the code, try different initial conditions to see what it will do. And just kind of make sure that you have an initial condition that makes sense, that it's periodic and that it integrates to 0. Though you can actually try it where it doesn't integrate to 0, but then the math of why it's working is a little bit more complicated than what we've been talking about. Okay, so now I think I'll explain what that extended system actually is, and that kind of depends on the homework. So I'll be back in a minute. Okay, so now we're going to talk about solving ax equals b in a very particular setting. So in our setting, we want a to be given by the 5-point stencil. On periodic grids. Okay. And so on a periodic grid, one thing that you'll know about A is that it has one entry, which is -4, and there are 4 other right, the -4 is on the diagonal, and there are 4 other off-diagonal entries which have the value 1. Okay. So in particular, if you apply A to W, where W is the vector of all 1s, AW equals 0. In particular, this matrix A has a non-trivial null space, so it's not, strictly speaking, invertible. In the homework, I have you kind of figure out the steps required to be able to invert a system like this. So in the homework, you show that A plus W transpose X equals B will actually be, right, this system is invertible. And if B is in the range of A, then AX will equal B. Okay. So on the homework, I have you show why all of that is true. And also, one problem with this is that the 5-point stencil is sparse. Okay. So because it's sparse, we can use the kind of nice built-in LU decomposition for sparse matrices that MATLAB has, which has a much faster running time. Once you add WW transpose, right, WW transpose just looks like a matrix of all ones. Okay. Maybe I'll label that. Okay. So that matrix is completely dense, and when you add it to A, you end up still with a dense matrix. Okay. So that's not great in terms of speed. So the trick is that you can actually embed this in a larger system. Erase this. And the solution of this system is the same as the solutions of this system. And in particular, this shows why in the code, right, we add that little 0 to the end of omega when we're solving for psi. The better thing about this extended system instead of the original system where you've added WW transpose is that this is still sparse, okay, because A was sparse. And then these W and W transpose vectors, while they're full vectors, are just vectors, right? So they just add n entries here and n entries here, so it's still a sparse matrix. Okay. And then within the code, right, I form this matrix, and then I call the LU decomposition on it so that each new solve is fast. So that's really kind of the whole thing with this extended system, and actually a lot of the pieces rely on the work that you've done in the homework. Okay. So I think that's all I'm going to say about that, and yeah, I'll see you next time.